Most rockets are produced by commercial companies. They make money by launching other companies' communication satellites, CubeSats, telescopes, science experiments, and more. All of these are launched on mostly autonomous or completely autonomous rockets. Astronauts are only used when the cargo is astronauts. This is because astronauts are just dead weight because they can't do anything that a computer can't do, and computers can perform most of the tasks better than they can. In this video, we are going to be talking about ULA, Rocket Lab, and SpaceX. ULA stands for United Launch Alliances, and they are one of the oldest rocket companies that still exists. SpaceX and Rocket Lab are newer, while SpaceX is the elder of the two. SpaceX and Rocket Lab both use more advanced manufacturing techniques, so their rockets are cheaper. ULA, on the other hand, has no failures, so the extra cost of ULA rockets is basically insurance that your rocket won't fail. NASA, on the other hand, makes worse rockets because every branch of the government wants their rockets to do a different thing. Then the rocket is trying to do too many things and ends up failing at all of them. NASA rockets are also more expensive because they are manufactured in many different states. In order to get funding, NASA will bribe states by putting manufacturing facilities in those states, which creates more jobs in those states. Also, after every election, when NASA is trying to do changes, so a lot of the work done by NASA is rendered useless by the time of the next election. One very cool rocket is the Delta IV Heavy. It is produced by ULA and is the successor to the Delta IV. The Delta IV Heavy is essentially a Delta IV with 3 times the number of liquid-fueled boosters and no solid rocket boosters. The 2 radial boosters run out of fuel before the central one because the center core throttles down shortly after launch. After the side boosters run out of fuel, they fall back to the Earth and are destroyed. Both the boosters and the center core use RS-68A engines. The RS-68A is the successor to the Space Shuttle's RS-25. The RS-68A has a higher thrust than the RS-25, but it has lower efficiency. The RS-68A is the world's most powerful hydrogen-fueled rocket engine, but it is also an open-cycle engine. The RS-68A is also cheaper than the RS-25 because its nozzle is ablatively cooled, not regeneratively cooled. The RS-68A uses hydrogen and LOX as its propellants. At sea level, its specific impulse is 362 seconds and has 411 seconds of specific impulse in a vacuum. The RS-25, for comparison, had 366 seconds of specific impulse at sea level and 452 seconds in a vacuum. The RS-68A also produces 3.136 kilonewtons of thrust, or 705,000 pounds of thrust. Something that the Delta IV is famous for is the massive fireball that appears at launch. That is because the RS-68A and all other hydrogen-fueled engines run fuel-rich before ignition. This is because if the chamber is not completely full of hydrogen when the oxygen enters, then some of the oxygen will not combust and will start corroding the combustion chamber. Hydrogen does not corrode the combustion chamber, but some of the hydrogen will escape the combustion chamber and rise out. Then a spark will ignite the hydrogen and make the fireball. The RS-68A, like all other hydrogen engines before it, does not burn at the perfect mixture ratio. The perfect mixture ratio is when you have the exact amount of hydrogen and oxygen in the combustion chamber so that it all combusts into water or another molecule. This is because burning at the perfect mixture ratio produces molecules with a higher mass than burning at a mixture ratio that is not perfect, so that would actually make the engine less efficient. Unburnt hydrogen, on the other hand, has a very low molecular mass and will bring down the average molecular mass to a point where the engine is actually more efficient. Once the center core runs out of fuel, the second stage, which has a hydrogen and LOX-powered RL-10B2 engine, fires. The RL-10B2 produces 465 seconds of specific impulse in a vacuum. It also produces 110 kilonewtons of thrust, or 24,729 pounds of thrust. And it has a 4.1 meter long nozzle, which is 163.5 inches. The RL-10B and all other RL-10 variants are considered to be one of the best vacuum engines ever. The Delta IV Heavy can bring 28,370 kilograms, or 62,540 pounds of payload to low Earth orbit. It is not used very often because hydrogen is very expensive and very hard to store. That is why the RP-1 and LOX-powered Atlas V is used more frequently. Also, you can't put crew on the Delta IV Heavy because of that massive fireball. The Atlas V is ULA's replacement to the Delta IV. The Atlas V is cheaper to produce due to its use of RP-1 as a fuel over hydrogen. You can also put crew in it because there is no fireball at launch. The first stage of the Atlas V uses a closed-cycle RD-180 engine. The RD-180 has a twin nozzle and a twin combustion chamber, but only a single turbopump. The turbopump in the RD-180 runs LOX-rich. It has 313 seconds of specific impulse at sea level and 339 seconds in a vacuum. As you can see, this is a serious performance drop over the RS-68A. That is because of the fact that the RD-180 is powered using RP-1. The RD-180 produces 3,830 kilonewtons of thrust at sea level, or 860,000 pounds of thrust. It also produces 4,150 kilonewtons of thrust in a vacuum, or 930,000 pounds. As you can see, the RD-180 has less efficiency, but more thrust than the RS-68A. The second stage of the Atlas V has one or two RL-10-1 engines, which is fueled using hydrogen and LOX. It is very similar to the RL-10B2 engine, so there is no need to go over it. The Atlas V can bring 9,800 kilograms, or 21,000 pounds of payload to low Earth orbit. This is significantly less than the Delta IV Heavy, but it is still a pretty large number. SpaceX is a company that is best known for reusing the spent stages of their rockets. The rocket that SpaceX uses the most is the Falcon 9. It is the successor to the Falcon 1, which is no longer being produced. The Falcon 9 is a Falcon 1 that has 9 engines on its first stage instead of 1. SpaceX uses cryogenic LOX and -6 degrees Celsius RP-1 in their rockets so that they can increase the density of their propellant. They also use nitrogen-powered cold gas thrusters for maneuvering in space. During booster recovery, spent boosters do a hover slam using only one of their 9 engines. A hover slam is a maneuver where a rocket hovers, then shuts off its engine and hits the ground. Before that, the boosters will either do a boost back burn so that they can land at the launch site, or will land on a drone ship. They can't land their boosters in the water because salt water is corrosive and will destroy their engines. During re-entry, the boosters slow themselves down using engines and steer themselves using grid fins and cold gas thrusters. Grid fins are fins that have been arranged so that they are interlocking. The engine relights itself multiple times using TTEB. The engine used by SpaceX is a Merlin 1D engine. Each of the 9 Merlin engines produces 845 kilonewtons, or 189,963 pounds of thrust at sea level, and 914 kilonewtons, or 205,475 pounds of thrust in a vacuum. The Merlin engine's thrust-to-weight ratio exceeds 150, making it the engine with the highest thrust relative to weight ever. The first stage of the Falcon 9 also has multiple engine-out capabilities. It can still complete its mission after losing 2 engines, depending on when it loses those engines. The specific impulse in a vacuum is 311 seconds, and at sea level it has 282 seconds of specific impulse. The Merlin engine also uses a Pintle injector. The second stage of the Falcon 9 uses a Merlin 1D vacuum-optimized engine. It's the same thing, except it can't be fired at sea level. And it produces 934 kilonewtons of thrust in a vacuum, or 210,000 pounds of thrust in a vacuum, and has 348 seconds of specific impulse in a vacuum. SpaceX's fairing can deliver craft with total volume equal to that of a school bus, and can deliver 22.8 metric tons, or 25 imperial tons, to low Earth orbit when fully expendable. Also, it can bring 13.2 metric tons, or 14.6 imperial tons, to low Earth orbit when reused. The Falcon Heavy is a very similar craft to the Falcon 9. It is the same craft, but with 2 Falcon 9 cores strapped to the side of it. Just like with the Delta IV Heavy, the center core will throttle down shortly after launch so that it can go farther. The two boosters will land themselves almost simultaneously. The volume that the Falcon Heavy can carry is the same, but the mass, when expended, is 63.8 metric tons, or 140,660 pounds. It can also carry 30 metric tons, or 33 imperial tons, to low Earth orbit when fully reused. Another SpaceX spacecraft is named Starship. Starship is the upper stage of the Starship rocket. The first stage is named Falcon Super Heavy, while the second stage is named Starship. Falcon Super Heavy has 37 Raptor engines, 6 landing legs, and 4 grid fins. The Raptor engine produces 2,000 kilonewtons, or 440,000 pounds of thrust at sea level. And it also has a thrust-to-weight ratio of 107 to 1, has a specific impulse at sea level of 330 seconds, and a specific impulse in a vacuum of 350 seconds. The Raptor engine also has the highest chamber pressure ever of 300 bar. The Raptor engine will also be one of the only methane-powered engines, and it was the first full-flow staged combustion cycle engine to ever fly. Falcon Super Heavy is supposed to be able to land itself just like the Falcon 9. Starship is the reusable upper stage of the rocket. It performs a controlled reentry using actuated air brakes for control. Actuated air brakes are air brakes that can be moved to change the amount of drag acting on the vehicle. They work by making one side have more drag, so that it goes up and rotates the craft. Actuated air brakes can control every axis except yaw. Starship uses a regenerative heat shield. The body of Starship is the payload fairing, and has parts that are on hinges so that it can open and close like a mouth. Starship uses 3 vacuum-optimized Raptor engines and 3 sea-level optimized ones. The 3 sea-level ones are mainly used to land it. During landing, Starship does most of this descent using air brakes and flips over at the last second and propulsively lands. Starship can deliver 100 metric tons to low Earth orbit, and with several orbital refuelings, it can bring another 100 metric tons, or 100 imperial tons, to either the Moon or Mars. When it goes to Mars, it has to bring an ISRU, also known as an in situ resource utilization. This will use the Martian atmosphere to manufacture methane and LOX, although it has to bring its own hydrogen to help with the manufacturing of the methane. Finally, there is Rocket Lab's Electron rocket. The Electron rocket is a small sat launcher, which means that it is designed to launch smaller payloads. When someone tries to launch a small payload on a large rocket, then the small payload has to ride with a larger payload. This means that the smaller payload is often ignored because the larger payload is owned by the people who are paying more money, and money is key to everything in life. On the other hand, the Electron rocket can launch within months of being informed of the need of having a launch. This is much better than the years of wait that would occur if you tried to launch using SpaceX or ULA. That being said, the Electron rocket is tiny at only 17 meters or 55 feet tall. It is also only 1.2 meters or 4 feet wide. Despite that, the Electron rocket is very advanced. Its bulkhead is made entirely out of advanced carbon composites, which has one of the highest strength relative to density of any material. This is the same material that racing skis are made out of. The Electron rocket's Rutherford engine is entirely 3D printed, and the process only takes 24 hours. It is the first engine to be entirely 3D printed. The Rutherford engine is also the only engine that uses an electric turbopump. This allows for much faster ignition and shut-off times. Each Rutherford engine runs on RP1 and LOX. They produce 21 kilonewtons, or 4,611 pounds of thrust at sea level, and has 303 seconds of specific impulse at sea level. 9 of these engines power the first stage of the Electron rocket, and 1 vacuum-optimized Rutherford engine powers the second stage. The vacuum-optimized engine produces 22 kilonewtons, or 5,000 pounds of thrust in a vacuum, and has 333 seconds specific impulse. The Electron rocket also has an optional third stage that produces 27 pounds of thrust. It uses an unknown green monopropellant as its fuel. It's capable of multiple relights and is also 3D printed. The Rocket Lab is looking into recovering their first stage. This stage would re-enter with a hypersonic ballute deployed. Hypersonic ballutes are balls that are attached to a high-strength wire and are jettisoned from the side of the rocket. The wire remains attached to the rocket and exerts a force on the rocket because of the ball's drag. This slows the rocket down so that it does not burn up. Then the wire is cut and a parafoil is deployed. A parafoil is a lifting surface that is also a parachute. Finally, the rocket is caught in midair by a helicopter. The Electron rocket could bring 225 kilograms or 496 pounds of payload to low Earth orbit.